This is Lab 2, the motion of a falling object. In this lab, I took a video of dropping an empty wallet from an estimated height. Then I took this video and using Tracker, I analyzed the results. Then, in order to find the actual values that would have come from experimental data, I used a computational model from VPython. In this computational model, there were two different scenarios. The first one involved a net force, which was the gravitational force of the Earth, otherwise known as the weight force, and the second one was the weight force plus the force of drag, or air resistance. Both models worked, but the model without drag overpredicted the values. I then analyzed some physics principles, including Newton's second law, and did a comparison between the predicted and observed data using a graph. This is a picture of a 200-gram wallet being dropped by a person of height calibrated at 1.702 meters. The wallet starts at the origin and goes down the y-axis until it hits the floor. The center of mass was calculated from the center of the object in each frame. These are some of the video analysis results. The observed start time was 0 seconds and the last time was 0.663 seconds, so this was a relatively short amount of time. The ball initial position was very close to 0 and the ball initial velocity was 0. As you can see from the bottom of this page, this was the data inputted into VPython. Another example of the use of VPython was delta t, which was very small, as seen it was 0.01. The proportionality constant g was given a value at 9.8, and the proportionality constant b for the magnitude of drag force was set to equal to 0 in the model without drag, giving the drag a force of 0. But for the second model, b was found by guess and check until the final position was equal to the value found in the experiment. This was the information used to calculate the while loop in VPython, and for the first model, you only used w for fnet, and this was because it only involved the weight force, which was the mass times gravity constant, which was 9.8. But for the second model, it was the addition of the weight constant plus the drag force, which was found using the equation negative b times the magnitude of the ball velocity times the ball velocity. The fundamental principle used in this experiment, as well as seen in experiment 1, was Newton's second law. This is velocity final equals velocity initial plus the net force times delta t divided by mass. As you can see, these equations were manipulated and put into VPython. These are the graphs that were shown using the computational model on VPython. The yellow arrow at the bottom of the screen is the weight force, while the blue arrow is the drag force. The magnitude of the weight force is greater than that of the drag force. This was the graph seen by taking the model versus experimental data. The blue dots are the experimental position that were analyzed from using Tracker. The red line is the model position with the drag, and the orange-yellow is the model position without the drag. As you can see, the model position without the drag overanalyzed the position, which means that the model position with the drag was the better model to be using in this experiment. Error seen in this lab comes from the misrepresentation of the center of the wallet. Because, as we had talked about, the time of this lab was very, very short, each frame used in Tracker had the image as a blur, and it was very hard to find the center of the blur in each different frame. What does it mean? Terminal velocity is the velocity of an object when the sum of the drag force and buoyancy equals the downward force of gravity, otherwise known as the net force equals 0. The first model will not predict terminal velocity because the weight force is the only force acting on the object. The second model will predict terminal velocity. This will be when the upward drag force is equal to the downward weight force. The object will travel with constant velocity until the object reaches the floor. What if? For the second model, the terminal velocity will be different with the non-zero initial velocity than when the object was initially dropped from rest. The object will reach the ground harder and faster than before. The terminal velocity will be reached sooner. In conclusion, this was the falling motion lab, and the model with drag force and weight force accurately describes the data. Thank you for watching my video.